Okay, for this quiz video, it's going to be entirely conceptual, so I've gone ahead and included two questions, both of them basically just finding directions. Now, this is going to be related to Section 3, Faraday's Law, and you should know this because there exist loops that are not connected to batteries. There is a solenoid connected to a battery here, but look here, you can see there's a loop right there that is not connected to a battery, and the question is going to be about that loop. And then there are these other hoops that are not connected to batteries that indicate, hey, we're probably going to have some generated EMFs. Okay, so take a look at them and see what you can come up with and compare your answers to mine. Okay, so let's start with the one on the left here. I'll just divide these right down the middle. And on the one on the left, we have a situation where we have a battery and a switch. The switch is disconnected at the moment. When the switch becomes closed, it will allow current to flow. What we've been asked is when the switch is closed, what will be the direction of the current in the resistor? Will the resistor have current backward or forward? Okay, so once the switch closes, we see positive is on the right, therefore current will flow up this side and down this side. If that's true, there are two ways to look at this solenoid here. One of them is grab the wire down here, and you'll see that your fingers are going to the left behind it if your thumb is pointed upward. So we'll go ahead and put thumb up, and fingers are going to be pointed around, right? And you could even point the fingers like that if you want, right, on the other side of the wire, right? Okay, I don't know why I just drew a butt hand, but okay. So what that indicates is that behind the wire the field will be going to the left. Now that's true down here. It's also true on each of these segments here, right? The other way is to think of each one of these wraps or turns as a hoop and then solve it in terms of hoop with current going up in the front and down in the back. So either way, you're going to end up with the magnetic field is to the left. Inside the solenoid, they have placed an iron core that just makes the magnetic field stronger. Alright, so now our new question is, we've solved basically half of this question. What we need to know is not just the direction of the magnetic field in this core. We need to know what the direction of the induced current is over here. So after all of that has been said, we have determined that there is magnetic field suddenly induced in the core, like so. Now we need to concern ourselves with this hoop. You're a hoop. What are you going to do about the sudden magnetic field? You're going to try to oppose it with your own external field this way. In order to make that happen, we need to use the second right-hand rule again, but this time for the case of our fighting current, not in the case of our battery current. Our fighting current is going to have to be through the resistor this way in order to produce the field here that counters the new magnetic field lines that have been intruding upon this hoop. Okay, so that means that we would expect the direction of current through our resistor to be out of the page. I should probably write that more exactly as the current in our resistor. So there we go. Okay. Now the next one, and if there's anything that isn't clear about that, email me. Let me know. All right. So the next one. Okay. Let's look at this again. We have a current going up. This one's actually a simpler system because we don't have to deal with a solenoid, but the application of these hoops is a little bit more perhaps tricky. So the system is simply a conducting straight wire. We know, therefore, that the magnetic field that is being generated by this current here, and which each of these hoops is going to feel, is by using the second right-hand rule. Grab the wire, your thumb will go up, your fingers will go around and to the left behind it, which means that they have to continue wrapping around and will come out of the page here and will go into the page on the other side and continue in that direction. Okay, so what that means is that our external field on these two is going to be out of the page, and our external field on this one is going to be into the page, right? So you, as the hoop, now have to decide what you're going to do about it. You need to create a field to counter the change. Okay, so let's take a look at A. Right now, there is a field pointed out. When we move the hoop upward, then what's going to happen here? I can actually move it upward. Let's move it. Move hoop. When I move it upward, I'm not actually changing the magnitude of the magnetic field. Now, think about it this way. If we have external field, and a certain amount here, and then a weaker amount here, and then a really weak amount out here, then if we move along this line, we're not changing the magnitude of the magnetic field. We're just coasting along the wire, right? And therefore, there is no change in magnetic flux through our hoop, and therefore, the induced current would be 0. There would not be any induced current in A. Now let's look at B. As you can see, we have this strong field here, weaker field out here, and even weaker field out here. So as we move hoop B to the left, then we should be experiencing less and less flux through our surface. Okay, so we ask our 3 questions. Number 1, what direction is the field going? It is pointed out of the page for loop B. 2, is it increasing or decreasing? Well, we're moving away from the wire to a weaker region, so it is decreasing. And 3, we want to know, what are we supposed to do about it? Well, you're the hoop, right? What are you going to do about it? You're not happy about the fact that you had all these, like a million flux lines coming out of the page, and now you have maybe like 100,000 or something like that. So you need to produce more flux lines out of the page, right? More field lines. So that is going to be then your response. Produce a response field out. Okay, and now all you have to do is figure out what direction of current will accomplish that. In order to produce a field out of the page, you will need to move current in this direction. Okay, let's do that same process over here for C. We need to answer these questions. We'll say, number 1, is the flux in or out of the page? Well, in this case, it's actually into the page. 2, is it increasing or decreasing? In fact, it is still decreasing. We're going the opposite direction, but we're still moving away from the wire. We're going from a place of very strong magnetic field to a place of very weak magnetic field. So, again, we ask, what are you going to do about that? Well, in the same as before, we need to produce field lines to compensate for the loss of the field lines we had before. But the field lines that we're losing this time in our hoop are pointed into the board. So you had a million going into the board. Now you've got like maybe a couple 100,000. You say, oh, I need to produce more field lines into the board to make up for the lost ones, right? So you'll produce B field in. In order to do that, you'll have to induce a current that goes this way. Okay, let's clean this up a little bit so that it's easier to see the answers. Okay, here are my answers. If you got something different, go back and see where you and I started drifting apart in our logic.